You are watching session number 3 of the chapter Polymers. In the previous session, I discussed about some examples of addition polymers and condensation polymers. In this session, I am going to discuss more examples and the concept about elastomers and biodegradable polymers. So let me continue with the examples of polymers. Example number 12, I am going to talk about bakelite. Bakelite example I am going to discuss here, and we already know that bakelite is an example for synthetic polymer, and bakelite is an example for thermosetting polymer also. And bakelite is an example for cross-linked or network polymer, and now you remember bakelite is an example for condensation polymerization also. So I told you that when the particular polymer does not belongs to a single category of classification, it depends on all the 4 different classifications of polymers based on the character what it has. So in case of bakelite, I told you already, it is a kind of condensation polymer. So what are the monomers involved in that case? Okay, so the monomers involved are, I am going to write here, the first monomer involved is phenol. Okay, and one more monomer involved is formaldehyde. So one monomer is phenol and one more monomer is formaldehyde. We will draw the structure of that one. Phenol, benzene ring with the OH. If OH group is attached to one carbon of the benzene ring, and that is the phenol, and one more monomer is formaldehyde, that is the aldehyde. Okay, and the formula for formaldehyde is HCHO. Aldehyde, actually formaldehyde is the common name. Okay, and since we have one carbon here, as per IUPAC you can call it as methanol for this formaldehyde. So phenol and formaldehyde undergoes the condensation polymerization. It is thermosetting polymer, I told you that one, and the thermosetting polymer is nothing but that undergoes complete change after heating. Okay, and the bakelite is very good example for a cross-linked polymer also. I told you that cross-linked means we have a 3-dimensional structure and heavy branches we are going to see, and here I cannot represent how water molecule is going to be eliminated. When phenol is going to be reacted with the formaldehyde, we will get a middle structure or intermediate structure, we call it as a novolac. Okay, and when novolac, okay, let me write here novolac. Okay, and when this novolac is going to heated in the presence of formaldehyde, you will get a structure, and that is nothing but bakelite. So let me draw the structure of bakelite here, and the structure of bakelite I am going to draw, and we have a partial structure I am going to draw. This is one phenolic group and one more phenolic we have, and these two are linked by CH2, and here we have a CH2, and this will continue here. Okay, and here it will continue from this side, continue from this side, continue from this side, and if you take the braces or brackets with N, and that would be the structure of what actually bakelite. So try to know that one. Okay, so this is actually the 3-dimensional structure of bakelite. This is the repeating in it, and it is going to repeat in the right side also, left side also, and bottom also. So now you can imagine what would be the complete structure of bakelite here. Okay, so that we call it as what actually the partial structure of bakelite. Remember, bakelite you can also call it as the phenol formaldehyde polymer also, but a novolac is the middle stage what we are going to get, and by heating that novolac with formaldehyde, you are going to get a polycondensed product that we call it as the bakelite. And application part, since it is thermosetting, so therefore many handles of kitchenwares are going to be made up by this bakelite only. And if you want very hard and tough kind of a substance, and the bakelite is preferred one. And that is about the 12th example, bakelite. So now we'll see the next one. Next one is 13, and melamine formaldehyde. melamine formaldehyde polymer. So we'll see now melamine formaldehyde polymer and how it is going to be formed. So melamine formaldehyde. So here first I am going to draw the structure of melamine. Just like benzene, but 3 carbons are replaced by 3 nitrogens here, and of course alternative double bond and single bond you are going to get, and this will be NH2, left side NH2 and right side NH2. So this is melamine. And one more, I told you that what is that actually? Formaldehyde, HCHO. Large amount of these we are using. Okay, so don't forget that one, because large number of monomers unite, you are going to get a polymer. So this is also what actually condensation polymer. So there will be elimination of simple molecule like water. So NH2 in general. Okay, we can remember H and OH from this, and that will unite. You are going to get the condensation polymer structure. So here I am going to draw the structure of the polymer obtained by melamine and formaldehyde. So as same, just like the same one I have drawn. So here INH I will write. The polymer will continue from the left side like this, and below I will write NH, and this also continues below, and in the right side, you know, I am going to write NH and CH2. This CH2 is going to be intaken from the formaldehyde, and that will be the partial structure, and I am going to write N. So try to know, in this case, left side, right side and the bottom we are going to extend the repeating units, so that you are going to get a polymer. We call it as melamine formaldehyde polymer. Okay, and the main property of melamine formaldehyde polymer is this is resistance to oil. You just try to know that one. It is very hard and tough, and resistance to oil. It won't react with that one, and in that case the best polymer suited is melamine formaldehyde, and that is an example for condensation polymer. So we'll see the next one, that is the last one, and we are going to talk about urea formaldehyde. Urea formaldehyde polymer. Here in these two cases actually the union of monomer name itself will be the name of the polymer. So melamine and formaldehyde, and this is formaldehyde. I am going to write here formaldehyde, and you are going to get that one, and the last one will be melamine formaldehyde polymer. Melamine formaldehyde polymer. The names are to be written. Okay, it is good if you write the names of the monomers and polymers. So now you can understand how you are going to get that, you know, urea and formaldehyde. Urea, known compound, NH2CO NH2, that will be the formula of urea, and large amount of urea. When it reacts with formaldehyde, HCHO. Okay, and it is also condensation reaction, removal of water takes place. Okay, and now I am going to write it directly. NH, it will extend from here, and CO we have, and NH we get, and CH2 from that formaldehyde, and I will put brackets and I will write N. Okay, and now I hope you can guess, in the middle of the polymer we have CONH, and I told you that one, if the repeating units are linked by CONH bond, and the kind of polymer we call it as polyamide. So urea formaldehyde is an example for polyamide. So urea, and here I am going to write formaldehyde, and the name of the product will be urea formaldehyde polymer. So all these three examples what I discussed, one is bakelite, melamine formaldehyde, and urea formaldehyde. All these examples are the examples for condensation, polymerization. While writing the statement of all the three, you need to write the keyword, that is, for example, phenol and formaldehyde undergoes the condensation polymerization to get a three-dimensional structure. We call it as a bakelite. Similarly, melamine and formaldehyde undergoes the condensation polymerization to get melamine formaldehyde polymer. Similarly, urea and formaldehyde undergoes the condensation polymerization to get a polyamide. The name of the polyamide is urea formaldehyde polymer, that is also condensation polymer. So all these are the examples what I discussed. And if you just look over from example number 1 to example number 14, I have given examples for homopolymers also and copolymers also, polyamide, polyester, and I told you how to identify whether it is addition or condensation, and homopolymer or copolymer, and polyamide, polyester, and look over these examples what I have given. So this is all about the concepts about the examples of polymers. And now we'll see one type of polymer, that is elastomers or rubbers. Rubber. And rubber, the one more name is elastomer. And if you just recall the classifications of polymers based on the molecular force, we have 4 different classes, isn't it? One is elastomers, second one is fiber, third one is thermoplastic, and the last one is thermosetting polymers. These are the 4 different types of polymers based on the molecular force present in it. And here it is the first one, rubber or elastomer. And we know that already elastomer is nothing but rubber which has the property of elasticity. It can be stretched and it can be bent with a greater extent, and after releasing the force it regains its original shape. And the reason behind this property is the weak molecular force, and the name of the particular force is the weak van der Waals force. We know that one. So that is the fundamental concept. Already we know about that rubber or elastomer. So now we'll discuss about the different types of rubbers. So in case of rubbers, we have 2 different types. The first one is natural rubber. The first one is natural rubber, and one can guess the second one, synthetic rubber. Natural rubber and synthetic rubber are the 2 different types of elastomers or rubbers. And the meaning is quite simple. If the rubbers found in nature, especially in plants, and that we call it as natural rubber. Man-made or artificially prepared rubber, we call it as a synthetic rubber. Naturally we know we have a rubber tree and we will get a latex from that, and using that latex one can manufacture the natural rubber, and we'll discuss about that. Here we are going to talk about the structure and some properties of natural rubber. So first I am going to move with what about the monomer. What about the monomer? The monomer of natural rubber is, I am going to write here, that will be isoprene. Isoprene is the monomer of natural rubber. So isoprene will combine with one more isoprene and you will get a polymer, and that we call it as a natural rubber. And a very good example, or the one more name I can write here, that will be polyisoprene. So try to know, polyisoprene is nothing but natural rubber, and the monomer is what actually, that is the isoprene. Okay, and one more name I am going to write here, isoprene, or one more name is 2-methyl. 2-methyl 1,3-butadiene. 2-methyl 1,3-butadiene, and this will be the IUPAC name of monomer of natural rubber. So you just look over here. We have 2 names, of course, the same. One is isoprene, that is the common or trivial name, and the IUPAC name will be 2-methyl 1,3-butadiene. In the examination, if they ask name the monomer of natural rubber, you can write isoprene or 2-methyl 1,3-butadiene. Sometimes they ask write the IUPAC name, and in that case you need to write 2-methyl 1,3-butadiene only. So now we'll see the structure of that. 2-methyl 1,3-butadiene, but we have 4 carbons. right? Diene, okay, and carbon carbon double bond in carbon number 1 and carbon number 3 I am going to see. Okay, so 2 methyl 1 and 2 on the second carbon we have methyl group, and I am going to balance it further, and you are going to get what actually this will be the structure of isoprene or 2-methyl-1,3-butadiene or the monomer of natural rubber. This is the condensed formula what we have. And now I am going to write the bond line formula. Bond line formula for isoprene or 2-methyl-1,3-butadiene, and I hope you know bond line formula is nothing but representation of organic molecule or organic compound using only chemical bonds. We are not supposed to write the element symbol here. So now what would be the bond line formula? How many carbons are in the linear chain? 1, 2, 3, 4. So I am going to write 1, 2, 3 and 4. 1, 2, 3, 4. 4 carbons we have. In between carbon number 1 and 2 we have a double bond, and I am going to show here double bond. In between carbon number 3 and 4 we have a double bond, I am going to show here. On carbon number 2 we have a methyl, so I am going to write here, and this will be what actually the bond line formula of monomer of natural rubber, and that will be 2-methyl-1,3-butadiene, and that is about the monomer. We will see what is the chemical name of this natural rubber. See, chemical name of natural rubber or the chemical name of a polyisoprene. The chemical name is cis-1,4-polyisoprene. Cis-1,4-polyisoprene will be the chemical name of natural rubber. So we will see why it is called cis-1,4-polyisoprene, and here I am going to draw the polymer structure of the natural rubber, and here I am drawing this is the structure of natural rubber, and it is a polymer, we know that, CH2, and here we have CH2. It will extend from here and it will extend from here. I will place the braces and I am going to write N here. This will be the repeating unit, and this repeating unit will repeat in the left side as well as the right side, so that we are going to get the complete structure of a polymer, that is the natural rubber. Okay, so see what actually the isoprene stands for. Remember, in case of isoprene unit, total number of carbons will be 5. You just see here. So 1, 2, 3, 4 and 5 carbons you are supposed to see in a single unit of isoprene. Okay, and here this is the isoprene unit. 1, 2, 3, 4, 5 we have. Of course we have here 5 carbons we have. And here it is going to be extended, so therefore this I can call it as a polyisoprene. And now the question arises, so why it is called cis-1,4-polyisoprene only? And I hope you remember the geometrical isomerism or geometrical isomers can be represented in two different forms. One is cis and one more is a trans. Okay, and if you recall what is the meaning of cis and what is the meaning of trans, if identical groups are present on same side of a carbon-carbon double bond, we call it as cis. If identical groups are present on opposite side of carbon-carbon double bond, we call it as a trans. So try to know cis and trans, these are geometrical isomerism that is going to be observed usually when we have carbon-carbon double bond. So now look over here. Here we have carbon-carbon double bond, then we can say what actually whether it is cis or trans. So what I said, if you consider carbon-carbon double bond, this is one side and this is one side. If identical groups or the same groups are present on the one side of the carbon-carbon double bond, that we call it as cis. So here this is one group. Of course it is CH2 we have, and along with we have a very large group here, and CH2 we have, along with we have a large group here. So these two groups are present on same side of the carbon-carbon single double bond, that we call it as cis. Let us assume if I write CH2 here and H here, so this will be the one group, and this will be the one group that is present on opposite side of the carbon-carbon double bond, and that I say it as what actually the trans 1,4-polyisoprene. So natural rubber, the chemical name will be cis-1,4-polyisoprene. Remember, cis-1,4-polyisoprene is only called natural rubber. Of course we have trans 1,4-isoprene also. I will write here trans 1,4-polyisoprene. trans 1,4-polyisoprene we have, and this we have a new name for that one, and that we call it as gutta percha. But this is not a rubber, this is not a natural rubber, I can say here. So try to know, natural rubber is always cis, and if it is trans, and that we don't call it as what actually the natural rubber, and that is the chemical name, and why we are supposed to consider that structure, and why it is called cis 1,4-polyisoprene we have seen. So now we'll see what about the characteristics, what about the properties of a natural rubber. We'll say that now. What are the properties of a natural rubber? It is very simple. Okay, natural rubbers are soft and sticky. That is soft. They are too soft and sticky in nature. You have greater viscosity, and it has low elasticity. It has low elasticity. Elastic nature is very low, and low tensile strength. Low tensile strength. If you apply high pressure, it is going to break, and it is soluble in some organic solvents. It is going to be soluble in some organic solvents, and that is actually the properties of a natural rubber. So from latex, what you get, the natural rubber, and that is too soft in nature, that is sticky, low elasticity we have, low tensile strength we have, and of course that is insoluble in water but soluble in some organic solvents here. These are the properties of natural rubber. But these days we need rubber, okay, with better properties when compared to the natural rubber. Nowadays we need hard rubber, and what happens, the sticky nature will be very less as compared to the natural rubber, and we need greater elasticity property, we need greater high tensile strength, and that should be not soluble in any kind of solvent. So these are the required properties of rubber what we need. Then what to do? The natural rubber what we get, that has less application when it has these properties. So now what we are supposed to do? We are going to convert that natural rubber into a kind of rubber, and in that case that has exactly opposite of all these properties. Or in simple language I can say, I am going to improve the properties of natural rubber. Okay, and converting natural rubber into the new rubber what I told, and that we call it as synthetic rubber. So we are converting natural rubber into synthetic rubber. Why we are converting? Because we are going to improve the properties of natural rubber. So what we have to do for that one? Okay, so here we are supposed to go for, we call it as vulcanization of natural rubber. So vulcanization of natural rubber is nothing but the conversion of natural rubber into synthetic rubber. So what we have to do here actually? Okay, I am going to write here. We are supposed to heating of natural rubber. Heating of natural rubber with sulfur. You try to know, with sulfur at 100 degrees Celsius to improve the properties of natural rubber, and that we call it as the vulcanization of rubber. Very important concept here. So try to know that one. What we have to do? We have to take the natural rubber, and natural rubber has all these properties, we know that one, and we are supposed to improve the properties of natural rubber. What we have to do? We have to heat the natural rubber at nearly 100 degrees Celsius, and we are supposed to add one cross-linking agent. You try to know, and the cross-linking agent used is sulfur. So what actually it stands for? Let us assume this is the isoprene unit. I will take one more isoprene unit and I am going to link these two by sulfur, and that we call it as cross-linking agent. Remember, in vulcanization of natural rubber, the element used as cross-linking is sulfur, and we are supposed to heat that, and we are going to get a rubber, and that we call it as vulcanized rubber or synthetic rubber. And what is the properties of vulcanized rubber then? So the properties are exactly opposite here. So if you want me to write the properties of that, so what are the properties of vulcanized rubber? Here I am going to write the properties of vulcanized rubber. They are, hard, and they are non-sticky. Just see, that is exactly opposite of the natural rubber. hard and non-sticky, and it has high elasticity, okay, and it has high tensile strength, and one more is that is insoluble in any kind of solvent, and that is all actually the properties of vulcanized rubber. You can call it as synthetic rubber, or you can call it as the vulcanized rubber. Okay, and that is how we converted the natural rubber into synthetic rubber by a process. And what is the name of the process? That process we call it as vulcanization. And what actually we did in case of vulcanization, we just heated the natural rubber and we got very hard and tough rubber. Why we are supposed to go for vulcanization? To increase the physical properties, to increase the properties of natural rubber, so that we are going to get the very hard and tough rubber of required properties, and we have n number of applications of that. Okay, in simple language I can say highly vulcanized rubber, we call it as synthetic rubber. We'll see now the second type of elastomer or rubber, that will be synthetic rubber. And I told you already, synthetic rubber is nothing but highly vulcanized rubber, and we changed the properties of natural rubber and we got very hard and tough rubber, and that we call it as synthetic rubber. So the second one is synthetic rubber. And here the two very important examples I am going to discuss. The first one is neoprene. So remember, neoprene is an example for synthetic rubber. This is high vulcanized rubber, you can say synthetic rubber, artificially prepared. And the one more name is polychloroprene or neoprene. Okay, and polychloroprene, and we can guess the monomer of polychloroprene will be the chloroprene. And now we'll see what actually the chloroprene structure stands for. Chloroprene, and here this is the common name. Now I am going to write the IUPAC name. You will come to know what is the actual structure. 2-chloro-1,3-butadiene. 2-chloro-1,3-butadiene, that is the name of chloroprene. Okay, so now we'll see how actually it is going to be reacted. So I am going to write the structure of that one. 1,3-butadiene, it is many times I discussed the same structure. So 4 carbons we have, and 1,3 position double bond. 2-chloro, on the carbon number 2 we have chloro, and balance with the hydrogens what we are going to get. And that is actually the monomer, that is a chloroprene or 2-chloro-1,3-butadiene. And this undergoes the kind of polymerization. Since we have a carbon-carbon double bond and only single kind of monomer we have, and one can easily guess, this undergoes addition polymerization. So after addition polymerization, how you are going to get the structure of that? So here I am going to draw CH2 single bond CCl, the carbon double bond single bond is going to be interchanged, and we have CH single bond CH2, right side, left side we are supposed to extend and place braces, and N you are supposed to write, and this will be what actually chloroprene. Here it is a polychloroprene you can say, or you can say this is nothing but neoprene. Both are same, neoprene or polychloroprene, and this undergoes addition polymerization. I told you that one. Okay, and this is a very simple example for the synthetic rubber. Okay, and how to write the statement. Neoprene is obtained by addition polymerization of chloroprene. And remember, addition polymerization, you can call it as a chain polymerization also. Remember, the mechanism involved is a free radical polymerization, free radical mechanism. Therefore, you can also say that neoprene is obtained by free radical polymerization of chloroprene, because radical will be the initiation, propagation, and the chain termination takes place, finally you are going to get a polymer, and that we call it as what actually polychloroprene. And this is well with the oil resistance material, and many hoses and many instruments we are supposed to use this neoprene as the synthetic rubber. And when you compare the natural rubber, this is very hard and tough, and it is insoluble in any kind of solvent, and that is the first example what we have, and that is neoprene. One more example I am going to consider for synthetic rubber, and that will be Bunayan. Just see, Bunayan. It is almost similar to one more copolymer what I explained already, that will be Bunayas. Okay, so we discussed that. So Bunayan we have. So we'll see almost the same kind of reaction I am going to consider. In this case, Bu stands for 1,3-butadiene. We know that 1,3-butadiene. So that is the one monomer of Bunayan. And one more will be, if here it was S and we would have written styrene as the monomer, here it is N, and remember N stands for a monomer, and that is acronitrile. That is acronitrile. So try to know that one. I hope you are quite familiar with this one, because I used this already while explaining one example of polymer, acronitrile. And if I write the one more name, you will easily guess what would be the structure, and the one more name will be vinyl cyanide. So vinyl cyanide is the one more name of this acronitrile. We'll draw the structures of that one. 1,3-butadiene, 4 carbons we have, carbon number 1 and 2 double bonds, here CH2, CH and CH, and I am going to write a CH2. That is the structure of 1,3-butadiene, and a large amount N. Of course, I forgot here also, you need to write N. And when this will react with one more acronitrile, vinyl cyanide, we have 2 carbons with double bond, cyanide, therefore I am going to write a CHCN. Okay, so that is the one more monomer in case of Bunayan what we have. And now I hope you can guess, this undergoes a kind of a polymerization, that is the addition polymerization, particularly copolymerization. This Na stands for sodium catalyst I am going to consider here. So now I am going to join these two, and you are quite good in the polymer structures writing. Okay, CH2 and carbon bond, double bond is going to exchange actually CH2, and that is going to be linked with that CH2 and CH double bond, and here I am supposed to write CN. You can write above or below the same thing, and below I am supposed to write subscript N, and that would be the structure of Bunayan. Many times this has been asked, explain the manufacture of Bunayan. Remember, Bunayan is an example for synthetic polymer, and I told you right how to write the statement. Okay, so Bunayan is formed by copolymerization. Remember that one. Bunayan is formed by copolymerization of 1,3-butadiene and acronitrile in the presence of a sodium catalyst. You can write copolymerization here also. So these two are the examples what I can give for synthetic rubber, and one is neoprene and one more will be Bunayan. And now we'll see the last concept, that is biodegradable polymers. As the name indicates, biodegradable. If a polymer undergoes decomposition or decaying by the action of bacteria, that we call it as biodegradable polymer. Environmental degradation, environmental decaying or decomposition of polymer, that we call it as the biodegradable polymers. Here we have two very important examples, and we'll see the structure and the monomers of that. And one is PHBV, and one more will be nylon 2, nylon 6. We'll come to that later. So now I am going to talk about the PHBV. So PHBV is the best example for biodegradable polymers, because this undergoes environmental degradation, environmental decomposition. So what is the full form I am going to write here? That is the PHBV. That will be beta hydroxy butyrate co beta hydroxy valerate. This is quite lengthy, therefore frequently we call it as PHBV. That is a full form. If you want, I have written that one. Polybeta hydroxy butyrate co-beta hydroxy valerate is the full name of the biodegradable polymer PHBV. So now we'll see what are the monomers and what is the final structure, and similarly we'll see the one more example for that. Let me write the monomer of that one. So the monomer of here actually two monomers we have. I am going to write here. That will be 3-hydroxy butanoic acid. One is 3-hydroxy butanoic acid and one more is 3-hydroxy pentanoic acid. 3-hydroxy pentanoic acid. Two different monomers we have, and we will try to write the structures. Butanoic acid, but 4 carbons we have, and butanoic acid COOH, okay, and 3-hydroxy 1 2 3 on carbon number 3 we have OH group hydroxy, okay, and we'll balance with the hydrogen CH3. Here we get H and here we get H2. So that will be 3-hydroxy butanoic acid. When it reacts with one more monomer, what is that? 3-hydroxy pentanoic acid, okay, and here we have 5 carbons and pentanoic acid and 5 carbons with COH, 3-hydroxy 1 2 3. Where we have the functional group, we have to start numbering from that OH and balance with the hydrogen CH2 and H and CH2, n amount of this. So these two are the monomers. If we ask name the monomers, only write the names. No need to write the complete the structure of that one. And here the question arises, how you are going to get the structure of PHBV. And remember, PHBV is the best example for condensation polymerization again, and here it is not as easy. Just by joining these two we are going to get the polymer structure. So just look over here how the elimination of a water molecule takes place here, and this is not as easy as it seems, and you have to look over here how I am going to eliminate the water, okay. So H from this, the left, the first monomer, and OH of this. So try to know H from 3-hydroxybutanoic acid and OH from 3-hydroxy pentanoic acid. And of course here these two will join, and in the middle, you know, we are supposed to join the 2 carbons, okay, and here in the left side also you have to remove, and right side also you have to remove, and the left side this hydrogen is going to be eliminated. I will show with such kind of a wavy line, and right side this OH is going to be eliminated. So right hand is how you need to remember, and then you can write easily the structure of that one. So now you just see, when this hydrogen is going to be removed means this oxygen is going to be linked with the left side portion, isn't it? So how I am going to write? So oxygen is going to be linked, okay. We have CH3 that I will write below, and oxygen is linked with this carbon. I am going to write, and I will continue. CH we have, and we have CH2, and H is removed, and what you are going to get? You are going to get COO. You just try to know OH and CH3, you can interchange these two, and there is a link with the oxygen I have written. In this case, in the center part you just see here, H of this carbon and OH of this carbon means this carbon and this carbon has to be joined, isn't it? So after CO and CH will be this carbon, and left side we have CH2 CH3 that I will write below. CH2 CH3, see the left side I have written this carbon is this carbon, okay, and right side what we have CH2 and OH is removed and CO that will extend here, and place the braces and write N, and that will be the structure of PHBV, and that is biodegradable polymer. Usually in the previous examination they have not asked the complete reaction, they asked give an example for biodegradable. You can write PHBV as an example, okay, and this is actually the structure. And here in not the same case, that is HOH should be removed from the middle and the corner, that does not follow for all the cases here. Sometimes this kind of elimination also takes place, and you need to remember there is elimination of NH2, and that is the example for condensation polymerization. One more we'll see, that is the last one, and that is nylon 2, nylon 6. See, nylon 2, nylon 6. We discussed already nylon 6 and nylon 6,6. Okay, but they are not biodegradable. Nylon 2, nylon 6 is biodegradable. We'll see the monomers and structures for that one. And let me write the names first so that it will be easy for you. The one monomer will be glycine, and one more monomer will be caproic acid. Okay, glycine and caproic acid. So try to know these are the examples for proteins, or you can say amino acids. You will learn more about these in a chapter called biomolecules. So try to know glycine and caproic acids are amino acids. So what is the structure of glycine? CH2 we have in the middle, right side we have COOH, and here we have NH2. Actually, amino acid is nothing but the organic compound which has the COOH group and NH2 group. So if these two functional groups are present in any organic compound, and that organic compound we call it as amino acids, and amino acids constitutes what actually the proteins. This is the one the monomer, and one more is caproic acid, and that is also a kind of amino acid, and CH2 5 times COOH and NH2N, and here one can easily guess we have COOH and NH2, and we can easily remove the water from here. Okay, so minus NH2O. I am going to write the complete structure here. So NH and CH2 CONH here, OH from here and H from here, CONH, and CH2 5 times we have, and CO, and that is going to be extended here, and here I will write the brackets and N, and that will be what actually the nylon 2, nylon 6. Okay, and that is also one more biodegradable polymer. And now you can guess why we have the name 2 and 6. 2 number of carbons in one monomer, here we have 2 carbons. 6 number of carbons in one more monomer, 5 and 1 6. So that is about how nylon 2 nylon 6 is going to be formed. So nylon 2 nylon 6 is formed by condensation polymerization of glycine and caproic acid. And now I hope you can easily guess we have CONH, that is nothing but amide bond. So therefore nylon 2 nylon 6 is an example for polyamide also. So PHBV and one more is nylon 2 nylon 6 are the examples for biodegradable polymers. So in this session I discussed some examples and the concept of elastomers and the concept of biodegradable polymers. That's about session number 3, and that is all about the end of the chapter called polymers. Thanks for watching.